right, this is a question that a couple of people have asked about, and I thought maybe I should try to address. So we talked about how to estimate definite integrals using Riemann sums. And we talked about the idea that as you make more rectangles, your area under your curve estimate gets better and better and better. And so we kind of summarized it by verbally discussing the idea that the final definite integral is actually the limit as the number of rectangles approaches infinity, as you get infinitely many, infinitely thin rectangles, okay? A couple of the multiple choice questions have been asking questions that ask you to write a formal limit Riemann sum to find a definite integral, okay? I've never seen this on a free response. Usually this is like the last multiple choice, comes up maybe every other year or something like that. It's been a little bit more common the last couple of years though. There are a couple of questions in the progress check about it. Again, they're allowed to put this on the AP exam if they want to. I don't think it's super likely, but they're allowed to. So here's the idea. I usually will kind of make a sketch of what's happening here, okay? And so for example, you know, I've got my curve here, and it doesn't matter like if your picture is accurate or not. You just need a picture to kind of work with. So I'm trying to find an integral here between 1 and 3, okay? So what's going to happen here is normally when you find a Riemann sum, you're making rectangles, and these could be right-hand sums, they could be left-hand sums, they could be midpoint sums. It really doesn't matter, okay? Because as you get infinitely many, infinitely thin rectangles, they're all going to approach the same limit. So I'm going to deal with a right-hand sum here, and this should give you something that's kind of similar to what they're giving you. So if you remember, Forrester has you draw a strip. He has you draw one rectangle in your interval, okay? And I'm going to draw the rectangle at the end, okay? So later we're dealing with infinitely thin rectangles. But right now I'm just going to make a rectangle. And again, this is way overestimating, but the idea is I get smaller and smaller and smaller rectangles, the sum's going to get better. So what's really happening here is you want to write a dA expression for the area of one of those rectangles, and the area is the length times the width, okay? The width of one of these rectangles is going to be, if I let n stand for the number of rectangles, the width of one of those rectangles is going to be the length of your interval divided by the number of rectangles, okay? So if my interval length is 2 units and I want to have 10 rectangles, each rectangle would be 0.2 units wide, okay? So the width is always going to be the length of the interval divided by the number of rectangles, okay? So that's my width, okay? Now, over time, that will become infinitely small, and that becomes the dx that we use when we find a definite integral, okay? But again, when we're doing a Riemann sum, you know, maybe I'm breaking this up into 2 rectangles. Maybe I'm breaking it up into 4 rectangles. It's just going to be the interval length divided by however many rectangles you have, okay? The length is going to be the functional value at a particular point, okay? It's going to be sine of whatever that value is there. Now, if I have 10 rectangles, then each rectangle's width is going to be 0.2, 2 divided by 10. The points that I'm checking here are going to be basically the starting value. It's going to be 1 plus however far I want to go over, okay? And again, however far I want to go over is 2 over n, okay? That's the width that I'm going over, okay? However, that's only for the first one, okay? So I want to go over to 1.2, and I want to find sine of that. And then I want to go over to 1.4, and I want to find sine of that. And then I want to go over to 1.6, and I want to find sine of that. And so what happens is each new rectangle, you're going over 0.2 more. You're going over whatever this width is more. And so they use, on the AP exam, they're using a k variable. It doesn't matter, but they're using a k to represent first rectangle, second rectangle, third rectangle, fourth rectangle, and so on. So if I multiply this whole thing by k, when k is 1, I'd be adding just the width of one rectangle, and I'd be finding sine of 1.2. When k is 2, I'd be adding the width of 2 rectangles. I'd be evaluating 1.4. When k is 3, I'd be evaluating at 1.6, and so on, okay? So the height of each rectangle is going to be sine of 1 plus 2k over n, okay? And then we put all this together. So this is going to be a sum of the area of each of the rectangles, okay? One rectangle has a height that's sine of 1 plus 2k over n, and it's being multiplied by a width of 2 over n, okay? K is our counting value for our Riemann sum. So it's starting at 1 and it's ending at the number of rectangles. So if I'm doing 10 rectangles, we go from 1 to 10, okay? We're saying we have n rectangles, so we're going from 1 to n, okay? As I get more and more and more rectangles, this approaches the actual area under the curve. So if I take the limit of this as the number of rectangles approaches infinity, that would be the same thing as that definite integral, okay? And again, if you're going to list this out, when k is 1, you'd be taking sine, well, let's say you're going from 1 to 10. If k was 1, you'd be taking sine of 1.2 and then multiplying it by a width of 0.2. When k was 2, you'd be taking sine of 1.4 and you'd be multiplying it by a width of 0.2. When k was 3, you'd be taking 1 plus 0.6 and multiplying it by a width of 0.2, and so on. So you're really writing the formula for adding it up. Again, you need the width of your interval divided by the number of rectangles, n, and that's your width right here. You need your starting value right here plus the width times k, okay? And that's just getting subbed in for the variable in your function. All right, so hopefully that's a little bit helpful. Again, I don't think this is real likely on the free response part of the AP exam. However, certainly it was something that was in our reading. We didn't do a lot of problems with it this year, but it is an idea that we need to know that really a definite integral is the limit of a Riemann sum as the number of rectangles approaches infinity.